Math 2414, improper integrals. Discontinuous integrands. The second type of improper integral doesn't involve infinity on a lower or upper limit. It kind of involves it somewhere else. It involves it because your function might be infinitely discontinuous at a point over which you're integrating. What do I mean by infinitely discontinuous? I basically mean a vertical asymptote. You know, for example, if we had something like f of x equals 1 over x minus 3, there's one number that makes this discontinuous, and it's the one that makes the denominator 0. And we would have a vertical asymptote. Without getting into all the song and dance, the graph looks something like this. But that's what I mean by an infinite discontinuity. There's an x value that creates a vertical asymptote, usually because it makes the denominator equal to 0. And not always, but usually. So what are these types of integrals? Well, there's 3 types. They're all definite integrals. But the thing that separates them is where the point of the vertical asymptote is. It can either be on the upper limit, or on the lower limit, or somewhere in the middle. But you kind of attack them all the same way. Let's start with the first type. If f of x is continuous on an interval a to b, including a but not b, just a reminder, in interval notation, bracket means you include the number, parentheses means you exclude the number. So the function's good everywhere except at the very end at b. And the function is infinitely discontinuous at x equals b. In other words, it's a vertical asymptote. Didn't close my parentheses here. Then, if you want to integrate this function from a to b, you have to set up a limit. This kind of goes the exact same way as we did with the infinite integrals, with the limits, the integrals with infinite limits of infinity. You replace the number giving you a problem with a variable. So we're going to replace the b with a t. You work the improper integral, you work the definite integral, but then you take the limit as t approaches b. But we can be more specific here because we don't just have to approach it from both sides. Remember, when a limit approaches something that's finite, you're assuming that it approaches from both sides and they meet at the same place. We're only worried about between here. So if you think about this as a number line, here's a, here's b, we only need to worry about in between. So technically the t we pick would be there, and it would get closer and closer to b from its left side. So we only have to take the limit as t approaches b from the left, since we're coming in from the left side of b. Now this is assuming that the limit exists, so let me throw an asterisk on here. However, if your function is continuous on this interval, open at a, closed at b, so it's not continuous at a, but it is continuous at b, and infinitely discontinuous at the beginning, then it's pretty much the same thing. We set up a definite integral, replace the problem number, a, with t, the b is good here, calculate this definite integral, the integral from t to b of f of x dx, but then we take the limit as t approaches the number that was causing a problem, a. But if the problem is at a, then the t would be approaching it from the right. T is approaching a from the right. So we only have to do the right-handed limit there. Asterisk, assuming the limit exists. Or the third type is you're continuous on some closed interval a to b. And in case you haven't picked up on this yet, or you haven't been told, a closed interval is an interval that contains its endpoints. An open interval is an interval that does not contain its endpoints. Both of these are half closed, half open. Closed where there's a bracket, open where there's a parentheses. The words open and closed aren't accidental. They are taken from a branch of mathematics called topology. And if you think calculus is theoretical, oh my goodness, you should go study topology, which is what I studied in graduate school, which is kind of the underlying foundation of calculus. But I digress. If f of x is continuous on some closed interval from a to b, except at some point x equals c inside of this open interval, translation, you're good everywhere except some point in the middle. Not the a, not the b, we've already covered those. But at some point in the middle, some point between a and b without being a and b. Then to evaluate the integral from a to b, you have to split it at that discontinuity. So you do the integral from a to c of f of x dx plus the integral from c to b of f of x dx. Now keep in mind that both of these have a discontinuity either at the top or the bottom, which means you have to do this integral using the top technique or this integral using the bottom technique. It's like when we had the integral from negative infinity to infinity, we had to split it in the middle and then handle those two cases separately. Same thing here, except we split it not at some random point, but at the point that's causing problems. And then when we evaluate each of these, we would replace that with the t and then do the limit thing. So this is what the rest of the section looks like, trying to evaluate an integral that has a discontinuous point somewhere in its finite limits of integration.